All right, so we're just going to carry on with chapter three now. Um, Today we'll be looking at 3.4 and possibly 3.5. We'll see how that goes. And what we're doing here is we're finding a new approach to finding the relative maximum or minimum of a function if they exist. And so this is referred to as this concavity and the second derivative test. All right. So I think I briefly mentioned this last time. This is another potential way of identifying extrema in your function. And, in some cases, it's a little bit simpler than using the first derivative test. So each case is a little bit different. It's good to know that there's another way of doing this. Okay. So we start out by defining concavity. Okay. By the way, the second derivative, if you remember, is simply the derivative of the first derivative. Okay, we haven't seen a whole lot of that up to this point, but let me just quickly remind you, at least as far as the notation goes, if you have a function, let's say we'll do something simple, 4x cubed minus 3x squared plus 7x, the first derivative, of course, would be applying the power rule to each of these terms. 4 times 3x squared minus 3 times 2x to the first plus 7x to the 0 power, which is 12x squared minus 6x plus 7. The second derivative is just the derivative of the first derivative. You just applied the same rules one more time. And of course, this last one goes to 0. So we got 24x minus 6. And of course, if you wanted to keep going, you could take the third and the fourth derivative, although with polynomials, eventually you'll always end up at 0. But here we're focusing our attention on second derivatives. So the second derivative, you can think of it as the rate of change of the first derivative, okay, as x changes. All right, so that's what it is. It tells us how much the first derivative changes when x changes. And it's the properties of the second derivative that will help us understand where in a function we might find a relative maximum or a relative minimum. All right, so how does this work? So we're going to start by introducing the concept of concavity. All right, so functions can fall into one of two categories. And so here's what's happening. Over a given interval, we have concavity if, and let's look at their graph. Let's take a look and see what we notice. If you look at those tangent lines, they put those little blue tangent lines there. A couple of things to notice. As we increase x, the slopes are increasing. Okay. In the beginning, this one on the far left is slightly negative, and then it jumps up to positive, and then it's more positive. So as x increases, the slopes of the tangent lines are increasing. Now, we don't know what's going to happen outside of this interval, but for as far as we can see here, as x increases, the slope of the curve increases. And that means that in this interval, the second derivative is positive. Okay, because as x increases, so does the first derivative, as you can tell by looking at the slope of the tangent line. And that in turn means that the function is over this interval, we're going to call it concave up. All right. Now, by the way, some books also refer to this as convex. Just be aware of that. Okay. So here they're just going to stick with the concave up, right? Now, of course, if there's a concave up, there must be a concave down. What does that mean? All right. So here's how that one would work. Well, basically, everything works in reverse. Okay. So if you go to the right, if you notice the slopes are getting steeper, they're becoming more negative. Okay. So, I'll make the note over here on the right. As x increases, the slopes of the tangent lines decrease. Okay. In this case, they become more negative. And as a consequence, the second derivative is negative, and we say that the function is either concave down, or some books refer to it very simply as concave. Okay, so just be aware of that. And one more thing, they want us to notice that in terms of geometry up here, if you notice, it's like the function is actually sitting on these tangent lines. They're underneath it basically. Whereas down here, it's the other way around. The function is essentially hanging from them. Um, and so the tangent lines are all on top of the curve. And so in terms of geometry, if you were to connect any two of these points, the curve is always below that line. All right. And so that's another way to demonstrate whether a function is either concave up or concave down. Okay. So there's several different ways to prove concavity, but why do we need this? Because it will help us identify where we might have points of that are relative maxima or relative minima. Okay. So that's where this is going. So, although these definitions are fun, they don't throw things in here without a good reason. So, here's an example of a function that goes through a period of being concave up and down. All right, let's take a look at this thing. All right, so what do we have here? This is the function 1/3 x cubed minus x. And so now this is the graph. And you notice below this, so here's m equals 0. The first derivative is 0 at exactly that point. Here, it's 0 as well. So the first derivative in this region is positive. How can you tell? Because, well, you can tell just by looking at the tangent lines. But then eventually it reaches 0, and then all of a sudden it's the other way around. They're all negative. Okay. Um, but having said that, now if you notice over here, while they're all positive, the first derivative is positive, but it's shrinking as x increases. Okay. So in other words, as x increases, f of x decreases. And therefore, over this interval, the second derivative is negative. Okay. So like we set up here, here the slope is increasing. The second derivative is positive. Down here, it was decreasing. And therefore, the second derivative is negative. And that in turn means that over this interval, the function is concave down. Okay. And that's what it says here. But then all of a sudden, we hit this peak here. And now, even though these slopes are negative, they're getting less negative as we move to the right, and eventually they become zero. So in this range here, f prime of x is increasing, although it's negative. Now it's becoming less negative as x increases, which implies the second derivative is positive, which in turn means concave up. Now, if you notice now, what they did down here, I'm not sure how helpful this really is, but what they did was they took the graph of the first derivative of this function. And what they'd like you to see is that while the function is concave down, you see how the first derivative is shrinking. Even though it's positive, it's shrinking. And then in the range where it says concave up, the first derivative is actually negative, but it is getting larger. And that's what it means to be concave up. Okay. Now, after this, we don't know without having the rest of the graph, but as all we at this moment, all we need to know is what's going on in those two intervals. And so you can see how we can tell which region is concave up and which is concave down. Ultimately, it all comes down to the second derivative. Okay, now, yeah, so this is the same graph. Okay. Now, test for concavity. By the way, I forgot, I think I kind of glossed over this, but with all of this discussion, we're always assuming that the function we're looking at, the function of interest, is assumed to be differentiable over the interval, over the specified interval. Otherwise, none of this works, okay? Because if there are discontinuities or there's, a sharp break in the curve or something like that, then that's going to throw off our results. But that's what's going on behind the scenes. We're assuming that the function is differentiable, and therefore no breaks, no sharp points in the graph. If that happens, well, then all of this is fine. If not, well, that, sort of calls our results into question. So we're assuming differentiability over this interval. Now here, this is the test for concavity. How do I identify it with the second derivative? So it's pretty straightforward. If we find that the second derivative is positive everywhere in that interval, then the function is concave up in that interval. If it's negative, then the graph is concave down over that interval. Okay, so it's a very straightforward idea. So let's see. Ah, here we go. There's an example. Beautiful. Okay. So I think our first step is to, of course, draw this somewhere, maybe in Symbolab, and just make sure we understand what it looks like. All right, so it's 6 over x squared plus 3. Now that's interesting. So I have a feeling that the concavity will change on either side of this point. It's like a little mountain, 0, comma 2. And you can see that the slope is positive. It goes to 0 and then it goes to negative. Um, so let's see what happens. I'll see if I can put a little sketch in here. And that point is 0, 2. All right. So now here, what do they want us to do here? Well, they clearly want us to identify any points where the concavity exists, but also where it might change. Okay. Now, the other thing too is that this function is continuous actually in the entire real number line, so we don't have to worry about that. And so they want their strategy is to first find the second derivative. Now that's going to be a bit of a time-consuming process, but we can do it. We know how this works because, well, all right, well, let's see how it goes. So I'll tell you what, let's do this. All right, now we're going to need the chain rule, by the way, for this one. All right, so if you think of this as g of x could be this interior function x squared plus 3, and that would mean that f of x is x to the minus 1. Or we could leave it as 6x to the minus 1. That's probably safer. Okay. All right, let's do that. Now, f prime of x, in this case, let's do that first. Based on the power rule, and then f prime of g of x would be minus 6 g of x to the minus 2 power. And then we'd plug in the actual definition of g of x. Okay. And then the g, we still need a g prime of x. Uh, and you can see up here that if g of x is x squared plus 3, g prime of x would be 2x. So here is the answer. That's the final result. That's the first derivative. What about the second derivative? Okay, well, now we've got a product rule, and then we'll also need another chain rule. So the first thing I'm going to do is combine these a little bit. Yeah, we're going to need them both. All right, so let's do this. We'll start with the product rule and then we'll apply the chain rule. Now, the f of x is easy. F of x is now being defined as negative 12x, which means that f prime of x is just minus 12. Okay. But if g of x is x squared plus 3 to the minus 2, then g prime of x is the one that needs the chain rule. Because you've got you're applying this is your f prime of g of x, where now of course we've got to be careful of the letters that are floating around here now. Um, but you've got this function, its derivative is negative 2 x squared plus 3 to the minus 3. And then out here you have this g prime of x, which is the derivative of whatever was inside here. So you've got all four parts. You can plug them in. You've got negative 12x. So right here is where we'll substitute all of our values. Now here we've got negative 2. And then we still need g of x. F prime of x is just negative 12. All right, so let's just simplify this a little. This first and this last term, I can multiply together to get minus 24x squared. Oh, wait, there's a negative 2 here, so let's make that positive 48. Whoops, 48x squared. And again, that comes from multiplying this, and this. And then that leaves here x squared plus 3 to the minus third power. And then down here we have minus 12 x squared plus 3 to the minus 2. That's the second derivative. So we need, oh my God, look at this mess. So they seem to have simplified it a little, but what they need us to do is find where this is equal to 0. Okay, because if you notice when we went through this, every time the concavity changed, um, it happened when we had a horizontal tangent line. So let's see if let's go back to one of the graphs again. All right, so what they're going to have us do is set this equal to 0. Now they just said, oh, by the way, it's 1 and negative 1, but well, we can start by dividing out the constants. I'm going to multiply both sides by x squared plus 3 to the positive third power. So that causes this to be 1. Um, Actually, let me make a note here so you can later on, if you're looking at these notes, you might forget what I did here. Um, okay. Wow, look at this mess. Okay, it's a little bit better now. You've got 3x squared equals 3. I subtracted the x squared from both sides. Divide out the 3. All right, so oops, that's a 1. All right, well, that didn't be it proved to be too painful. So what they're going to have us do now is set up this little table and look at these, identify or figure out the value of the second derivative within each of these intervals. So if you go back to the original graph, the 2 points of interest are here and here. Okay. So they're going to have us check the concavity in these three regions here, here, and here. Okay. So now we can follow along with the box. In fact, we can copy the box. So they chose, again, the intervals are meant to be. So you notice what they've done in the chart. Negative infinity up to -1, -1 to 1, 1 to infinity. And so they just arbitrarily chose -2 here, 0 here, and 2 over here. And then we solve for the second derivative at that point. All we care about is not the value, but the sign. Now, since I've already done all the calculations, since this is a really messy function, we'll just take their word for it that, here f double prime of -2 is positive. But you can kind of see by looking at the shape, as you go from the left to the right, the curve is getting steeper. Okay, so that means along here, that implies a second derivative that's positive. And that means the function is concave up. And then in this interval, it's the opposite. It's rising and then falling. So it's kind of like a ball up in the air and then comes back down again. Here, the derivative is decreasing. And that implies the second derivative is negative, and that's concave down. And then it turns around. And again, it's kind of tricky to see it from the graph, but the derivative is flattening out. It's starting to get a little steeper again. F prime of x is increasing. But the fact, now here's the thing though, they're proving it not by looking at the graph, but picking a point in that interval. Because if this is true for that point, it'll be true for all the points in that interval. So that we know that after we get at past 1, f double prime is positive again, and that means concave up. Okay, So this is now, so far they haven't shown us how to tie this together with relative maxima and minima. So far, all we know how to do is identify the regions in which the function is concave up or down. Okay, but we'll get to that in a minute. Okay, we'll see. Don't you worry. And so, yeah, we'll just put this in here. Beautiful. Okay. Points of inflection. Isn't that interesting? More terminology. Well, what happens is the points of inflection are the points where the concavity changes. Here it goes from up to down and down to up. So these points are known as inflection points. Okay. So formally, by the way, it doesn't matter if we're going from concave up to down or down to up. We still call it a point of inflection. Now, if, by the way, this result is kind of interesting because it's saying that if we have the point C, f of C is an inflection point, then one of two things must be true. Either the second derivative is zero, okay, and here you can see why that would have to be because the only way we can go from zero positive to negative is that if it reaches zero somewhere in between. Okay, so in other words, even though it doesn't have that labeled at this exact point, uh, and here, same thing. To go from negative to down to up, the only way that can happen is if this point has a second derivative of zero. So in the problem where they insisted that we set this messy expression equal to zero, that was the reason, because what we actually found here are the inflection points. That's how we do this. Okay. And that's how you identify the intervals over which the function may be concave up or down. Okay. But it's, and this happens so often in calculus. It's possible too, though, an inflection point can occur um, when there's a very dramatic change in the shape of the curve, which could actually result in an undefined uh, second derivative. I don't know if they have an example of that here. Um, Maybe not. But they just want you to be aware that something like that could actually happen. Okay. Maybe eventually they'll bring out an example of this. But anyway, in the meantime, why don't we look at this case? So they want us to first find the points of inflection or inflection points, and then identify the concavity in the intervals that we define that way. So we start by taking the first derivative, using the power rule, and then the second, set it equal to zero. Oh, you know what? We might as well take a look at this thing in Symbolab so we can visualize what we're actually doing. Man, nobody would have guessed that this is what we had earlier. I mean, look at that thing. X to the fourth minus 4x cubed. Oh my God, look at that thing. Ooh. All right, well, all right, let's carry on. Um, Actually, let's not do it that way. Let's do this. First of all, we can divide out the 12s. So the points of inflection are at 0 and 2, right there and there. Wait, that's 4. What's going on here? Oh, I see. Okay, no, I forgot. Symbol Lab is labeling those because that's not why they're labeling them. There's a different reason for those labels. But anyway, so now what we're going to need to do, I'm going to take I'm going to try to graph this thing on the, oh my God. All right, that's the best I can do. 2 is going to be over here somewhere. So what we're going to need to do is test the sign of the second derivative in these intervals that we just created. In other words, we're going to look at the intervals. All right, so those are my intervals. And then we're going to pick some random point in that interval. And we did note here that the second derivative is here. So the boxes that they drew in the slides are set up in the same way. Let's go back and look at one. There it is. So you've got an interval, then you have test values, they're called. All right, so I randomly picked those 3 points because they're in that interval. And then we're going to find the sign of the second derivative. So like this one, yeah, there's not a whole lot of room here, so I'll have to be careful. Okay, so positive there. And then f double prime of 1 would be 12 times 1 squared minus 24 times 1. Then it goes to negative, and then f double prime of 3 is 12 3 squared minus 24 3. 9 times 12 is 108. Okay, so here's we are concave up. Okay, good. So I think that's all they asked us to do. Oh, so here's their chart. Yeah. In fact, just by lucky coincidence, we picked the same numbers. Yeah. So there we are. So this is what they're after. Concave up, down, and up. And of course, the 3 points, the 2 points, 0 and 2 are the inflection points. So hopefully, yeah, here it is. Okay, that's good. It's awfully hard sometimes to draw these graphs. It's always better when they give us one. All right. So you can see, I guess visually, that, clearly the function is up, down, and up. And well, there we go. Nice. Okay. So that's the end of that example. So here they're trying to show us a case where, um, oh, well, yeah, no, they're saying that just because the second derivative is 0 doesn't guarantee that it's a point of inflection. Because here, we've got a flat bottom here, which means the first and second derivatives are both flat or 0. The tangent lines are 0 or flat. So, but it is not an inflection point because clearly the concavity is not changing there. Okay. So we tie all this together to give us finally, after all that, the second derivative test. So if the graph of a function is concave up over an interval containing C, and the tangent line is horizontal, then f of c must be a relative minimum. So in other words, the combination of those two conditions is that um, so basically what they're saying is we already knew that if f prime of c is 0, then this point could be a relative maximum or a minimum. What When we first introduced this idea, we did not specify how to tell if it was a maximum or a minimum. We were just identifying extrema of either type. But now what it's saying is that the first derivative is 0, and in addition to that, the second derivative is positive. That guarantees that this is a relative minimum. Okay, so this part tells us that this is a relative extrema or extremum. And therefore, on top of that, knowing that the second derivative is positive tells us that it is a relative minimum. Down here, um, if we know that the second derivative is negative, obviously it's backwards. So I'm putting that in here to make sure because that might help us visualize why this is true. So just imagine some random function. So in other words, what's happening here is that the slopes of these tangent lines are getting smaller. So the second derivative is negative, which means this must be a relative maximum. And then down here is the opposite. Now, of course, this is a pretty terrible drawing, but oh, I'm sorry, this is positive. And that makes it a relative minimum. Okay. So in other words, it sounds backwards, doesn't it? Like a positive second derivative means that it's a minimum, and a negative second derivative means that it's positive. But that's why, because a positive second derivative means you're basically sitting on top of a hill, and down here, a negative second derivative means you're sitting at the bottom of a valley. Okay. So that's why the first one is a maximum, even with a negative second derivative. The second one is a minimum with a positive second derivative. Okay. Oh, don't worry, you'll get used to it. All right, let's see if they've got an example for us. So yeah, so the concave down, you're sitting at the top of a hill, so to speak. Um, the curve is you're going from a positive to zero to negative slope. F prime of x is decreasing. Second derivative is negative, and that means we must be at a relative maximum. All right, so assuming that the first derivative is zero, and the second derivative exists, of course, and some given open interval, then a positive second derivative means that this must be a relative minimum. A negative second derivative means it must be a relative maximum. Now, once in a while, and you always have to know if there's any exceptions to any rule in calculus. What happens if somehow we wind up with a second derivative that's not positive or negative, but it's zero? Oh my God. And we'll see eventually a case where that happens. Okay. Um, It sounds impossible, but it's not. Okay. If instead it's zero, then we say the test fails and we have to go back and use the first derivative test. Now, remember how that works. All you're doing there is looking at the sign of the first derivative on either side of that point. Okay. So like here we saw that on either side, the slope of the curve goes from positive to negative. That makes it a relative maximum. Down here, the slope goes from negative to positive, and that's how we know it's a relative minimum. That's the first derivative test. It always works. So if the second derivative test fails, we just step back and do the first derivative test. All right, here we go. Let's see. Oh my God. I shudder to think what they've done with this one. I'm hoping that they took it easy with us. All right, so they want us to find the relative extrema. Now, what we're going to do is just right off the bat, take the first and second derivatives. So remember how that works. That's where these are coming from. Okay. And then the second derivative, based on the same rule. And now we're going to set this equal to zero. Oops. Okay. We can first divide out by this. Let's divide out the negative 30. So now it's 2x cubed minus x equals 0. Now, of course, if this product equals 0, that means each term individually equals 0. All right, x is plus or minus. So the three um, points that we're interested in studying are 0. Um, we probably should rewrite this. We did this the other day. Um, we're rationalizing the denominator to avoid having a square root in the denominator. So we can say that the 3 points of interest are 0, negative radical 2 over 2, and radical 2 over 2. Great. So whoops, no, sorry, that's 0. Oh, no, we've got 4 intervals because there's 3 points. Okay. So then, of course, what you're going to do is check. Wow, this is a messy one. There's something's not right. Oh, no, no. Here, you know what they wanted us to do? They didn't, they're not having us check the intervals for the second derivative. They simply wanted us to find the critical values. All right. So this part wasn't necessary then. They wanted us to take this. All right. Because they're only interested apparently in the critical values or critical numbers. So we could just divide out this negative 15. All right, now what? Now on the left, technically that's plus or minus zero, but we don't have to worry about that. In the right, we have x squared equals 1. And that's when you take the square root, it could either be plus or minus 1. So we have three extrema, or critical numbers, I should say. All right, so I think what they're going to have us do now is test, uh, use the second derivative test to find out whether these are relative maxima or minima. So the second derivative we found up here. There we go. So we'll check out the sign at each of these 3 points. So that's going to be 60 minus 30 positive. I'll just do that again. All right, so this one's positive. Then we'll do the same thing for 0. Now 0 is very obvious. Oh, I bet that's why they did this. And then f double prime of 1. Okay, so the second derivative test fails at 0. So that means what we have to do is go back to the original function. I'm sorry, not the original function, the first derivative, and check out its value on either side of zero. All right, so we'll do this. We'll do f prime of -1. Ooh, it's zero. All right. Well, I think we better look at the answer then. I don't know what happened there. We have an issue with this curve, that's for sure. Yeah, well, they agree with us. I mean, the points are -1, 0, and 1. So we have a relative minimum at -1, which we already knew. Um, and oh, you know what? I just realized I wrote this incorrectly. This should have said relative max because it's negative. That's correct. The test fails. Oh, I know where I screwed it up. We were supposed to test the original function. Sorry about that, not the derivative. Um, so f of -1, the original function was, let's go grab the original function. Way back here, yes. Let's see. Oh, see now you can see right there from that graph. Um, they're trying to trick us. Yeah, you see it's not, yes, even though right at that point the horizontal axis the slope is zero. It's not a maximum and it's not a minimum. So that's why the second derivative test failed. But the first derivative test doesn't work either because you notice how the slope is positive on either side. So they threw a curveball at us here. That's why this didn't work out well. It should be positive on either side. So any way you look at it, this third point is not a relative maximum or minimum. Yeah, because, oh, but you know what I just realized? The reason why we had a problem is because I accidentally chose -1. That was too far over. That was one of the critical values. If I had used -1/2, okay, let's try that. I just want to check this real fast. Yeah, that because I made a bad choice here. It should have been something smaller. Like, yeah, that would do it. It won't be zero, in other words. And then on the other side, let's try f of positive one half. Yeah, you see, there's the problem. Positive, negative, it won't matter because these are both even exponents. It's going to be the same thing. So in other words, the first derivative test does fail. Both of the tests failed, and therefore it's neither. Okay. If they don't, neither one of them is going to pass. That, and you can see why, because it just sort of keeps going up. It sort of temporarily pauses almost and then starts to rise. So because both of those tests failed, this point cannot be a relative extremum. I better fix that. All right. So yeah, they threw a curveball at us. But we've had some good practice with this stuff. All right. So I'll tell you what we'll do. Now, what this is 3.4 still. 3.5. Let me just remind myself what's 3.5. Oh, okay. You'll like this. What they're going to do is sort of take a step back and look at limits again, but now we're going to be specifically focused on limits at infinity, it's called. Um, and then they're going to show us how to find horizontal asymptotes if they exist. We already know how to do vertical asymptotes. Those are the points where the function is undefined, but they're going to give us some rules for finding horizontal asymptotes. So I'll tell you what we'll have to do. Um, we clearly don't have time to do this right now, so I'm going to do this. Why don't we do these last two examples and 3.5 the next time we meet? Okay, I think this was very intense. There was a lot to think about. So we'll get together again. We'll wrap up the last couple of examples in 3, 4, and then we will do as much of 5 as we can. Okay. So, all right. So I'll see you next time.